Hi, I am Bitweasil, also known as Russ Graves, and I'm going to be talking about the Cryptohaze network architecture, which also includes a discussion of the entire design of the framework because the two are heavily integrated together. So I'm going to start with a little bit of background with how the entire Cryptohaze password cracking suite started. It began as a grad student, as it seems many projects here have. There was some discussion about rainbow tables and building very, very large rainbow table sets with some of the computers that we had for research and cyber defense competitions. And, well, what grad student can resist the thought of advisor paid for 8800 GTXs? CUDA was in its very, very early stages, but it was around, and I proposed playing with it. And it ended up being my master's thesis, and it has continued since then. So the password brute forcing tool that I have is the multi-forcer. I apologize for the names, I'm terrible at them. If anybody has better suggestions, find me later. Back in 2008, I actually started writing these as a pre-filter for the rainbow tables to deal with smaller password spaces that made sense to use a rainbow table for. In around 2010, it was rewritten as the Cryptohaze multi-forcer with a C++ framework. It was still CUDA only at this point. In around 2011, I played around with some of the network support because I realized that scaling single systems was going to be a problem sooner rather than later. And most recently, I have been working on the new version, which is the terribly named new multi-forcer, that is a C++ framework with CUDA, OpenCL, and CPU currently supported. And one of my big goals with this is to eliminate duplicate code. Those of you who have written or modified password crackers have probably dealt with the fact that a lot of the code tends to be copy-pasted with changed values, which tends to lead to bugs and things getting fixed in one place but not another. And so I've been striving to eliminate that as much as possible to make things work better. The reason that I support CUDA, OpenCL, and CPU right now is partly because of what's been happening with technology in the last 5 years or so. When I started back in 2007, CUDA was in its infancy. It had just come out with a 1.0 release. FPGAs were around, and I briefly considered them, but decided that the initial cost and the cost of building boards and the programming time made them probably not the best option. They very clearly have value, but how many of you own FPGAs versus how many of you own video cards? The cell processor was discussed quite frequently when it came out, and it did do really good. It was a fast option. Unfortunately, the cell processor today in the PlayStation 3 can't run Linux and hasn't gotten any faster. So finally, there were CPU options, and those continue. Today, we still have CUDA. It's much more mature. They happen to have cards that don't work very well for password cracking right now, but it actually is quite more enjoyable to program for. FPGAs are still an option, and I would like to add support at some point. I just don't have FPGAs, and they're a much lower priority than other technologies. The bulk of what's going on right now is Radeon cards and OpenCL, which is what the vast majority of tools support. We have much more interesting vector instructions now with the 256-bit vector operations. And finally, I don't know if any of you have looked at it, but Intel's Xeon Phi coprocessor has 512-bit vectors, and looks like it could be a very interesting architecture for password cracking. So the multi-forcer in its current state is a GPL v2 open source tool, currently supporting the 3 major platforms that most people use, with, as I mentioned, CUDA, OpenCL, and CPU support, written in C++. with the appropriate compute languages at the end. And at this point, it has integrated network support, which means I'm not relying on any third-party libraries such as VCL, NPI, or any of the cluster languages. I have the network support for it totally built in, totally under my control, and I'm not reliant on anyone else for bug fixes with that. So the code architecture that I'm using to do this is pretty standard object-oriented. And the reason that I'm doing this is to avoid as much recoding as possible. So for the hash file class, it involves reading the password files, which come in a variety of formats with a variety of different quirks. And so off of the base class, I have the plain hash class, which contains unsalted passwords. I have the salted class, and then I also support weird things for things like the IKE hashes, WPA, and things that have a lot of extra data with them. This is all supported in the base class, and the implementations come out at the various other nodes. The advantage of this, though, is that for things like the LDAP SHA hash, which is just a base 64 encoded hash with prefix, all I have to do is override a couple functions, and the rest of the hash file plain class handles it. The same thing for salted hashes. The SSHA and the IPB hashes are really just salted hashes, so I can either play with some ordering or just override the functionality to do the base 64 decoding. And then all of the common functionality lives in the lower layers, and it's harder to screw things up. Or at least when you do, you can fix it one place and be good. So for the actual logic that handles the password cracking in operation, I have a couple different levels. The base hash type class controls the bulk of the cracking logic, control flow, and just the general main process, because it's really almost identical whether you're using a CPU, CUDA, OpenCL, or potentially other devices. And one thing that I've added into the code is a concept of attributes that a hash can use. So some hashes need salt, some need a word list, some need different bitmaps. And the hashes can actually request these at instantiation, and the base class takes care of all of this. So it's really very easy to add new hash types to it. The next level up is the technology level, so CUDA, OpenCL, CPU, and this handles things like compilation of kernels at runtime, copying the bulk of the data to and from the device, and any other general technology-specific function. The next level would be the hash-specific instantiation on the host, and this basically serves as a transfer layer into the device kernels. It has the name of them for compilation, any of the constant values that they need, and just serves to shove data to the kernels, which hang out at the highest level and largely make use of some predefined blocks that I have. So it's mostly hash implementation and wrapping code around it. So again, to bring this down into a slightly more concrete example, these are some of the classes that I have. The hash type plain class extends up to the CUDA, CPU, and OpenCL classes. CUDA would expand out to the various hash types, each of which has their specific device kernel attached. Looking at the OpenCL version, we have pretty much the same thing, just from OpenCL. And again, the bulk of the code is down in the lower levels, so you can reuse that and not have to code things up for each specific hash type. Now, getting into some of the... There we go. Getting into some of the stuff that I've implemented that makes the network functionality much easier. I break work down into work units, and this is one of the standard methods of splitting a large task across a wide variety of devices or systems. I've had this support for quite a while because I support mismatched GPU types. And each work unit contains relevant information for its chunk of the problem, which could be the start point and end point for brute force. It also contains things like password length and flags, which are used to communicate with the individual cracking threads and essentially say, hey, we're done, or other threads are still working, so wait because you may get assigned something, or general other operations like that. I also include word lists into the work unit, which I will touch a little bit later. And each work unit contains a client ID for identifying which client has requested it. This is so that I can implement some of the robust functionality over the network, because unfortunately machines frequently go missing during the middle of a cracking operation, or crash, or the network disconnects, or Comcast decides that they're going to have an outage, or pick your problem. Nodes get disconnected, and the goal is, even in a highly unreliable environment, I want to be able to ensure that I have tried every possible combination that is specified. I don't want to lose work because of a network failure. So, the way that this is actually coded up, the generation parameters are stored in the work unit class, either word list elements, the brute force space, or anything else. This is done so that I'm not trying to allocate, say, 24 gig worth of work units when the program starts, which doesn't usually work. When these are requested, I cannot tap today. When these are requested by either a thread or a network client, they go into a pending queue. And this is where they live in the main work unit class while they're being run. They live there so that, the pending queue is work units that have not yet been assigned to a device. I keep a batch available so that they can be assigned quickly. When they are grabbed by a thread, they go into the in-flight queue, and this is where the client ID matters. If it is completed successfully, the work unit gets retired and removed. If the client crashes, disconnects, or fails to send a regular heartbeat, however, the work unit class will eventually receive a message from the network class saying this client ID has disconnected or timed out, and all of the work units from that client ID will be pushed back into the pending queue to be reassigned to a different device so that they can actually get executed. So that sets the base for the code foundation, which is basically sets up how I do my network architecture. You've got a cracking server, which specifies the process, and then you have the client, or more specifically multiple clients, that will connect to the server. And each class talks to its comparable instantiation on the other half. The character set class simply talks to the character set class across the network. Same for the hash file class, same for the work unit class. And this is handled by the network client and server classes, which simply shovel data back and forth across the network. The network class does not know what the hash file class is. It does not know which character set class you're using. All it knows is that this is the current in-use hash file class, and it can retrieve data from it. I have functions like this present, and I promise this is the only actual code that I'll stick on screen. Import hash list from remote system, export hash list to remote system. These simply grab a chunk of binary data or produce a chunk of binary data that is sent across the network, and the other class understands it. So it moves all of the complexity of serializing and deserializing data from the network class into these specific classes on either end. Conveniently, there are some very cool serialization libraries put out called protocol buffers. If anybody has dealt with network serialization in the past, it usually does not go well. XML is great, except for the fact that it's about a 10 times expansion on data. Some of the boost serialization libraries work, but again, they're not very data efficient, and when you're shuffling large amounts of data around the network, ideally you want something that's fairly efficient. Binary packing stuff yourself can work, except it's really difficult to write. It tends to be rather system architecture specific, and you get problems between 32 and 64-bit systems unless you're really doing a lot of work to make sure that you don't have those problems. So protocol buffers are a very efficient, binary-packed, machine-readable format. They're designed for computers to talk to computers. You can export an ASCII version, but this is not the normal. They're designed for computers to talk to computers. They are backwards compatible with optional fields. So if you choose to change your encoding or add additional fields, if they're optional, you won't break backwards compatibility, which is quite nice. And because each class is talking only to another instance of that class across the network, each class can have its own unique, custom-designed protocol buffer for the data that it needs to transfer. And again, as I said, the network class simply passes this data back and forth. One thing that I haven't added quite yet is compression in the network class, but there are some very good compression libraries that effectively compress things like word list data and will reduce the bandwidth requirements going across the network. This matters more for internet scale work than for LAN, but it's easy to add. So, that's the base of the network functionality. Next, I'm going to talk about the problem with word list support in some of the existing tools. And this is actually very, very relevant to the other talks today that are talking about creative ways to guess passwords. The problem has been varying maximum lengths are supported. In some cases, this is algorithm specific, in some cases it's architecture specific, but right now there's not a reliable way to run a long sentence through password cracking tools. Most of the tools support up to a maximum length of, say, 27 characters for NTLM, 55 for MD5, because this is what you can fit in one block operation. The sentence, "I am the very model of a modern major general," is probably not a good password, but it is also very unlikely to be cracked right now, simply because most tools don't support that. Also, most of the word list functions right now either deal with a single file source or a single input to standard in. If you've got multiple different sets of password guessing tools that you wish to use, you either run them sequentially or you can do some pre-stream merging, but there's not really a good way of doing it right now. And the network distributed support for word list stuff is just hard to work out. Some of the solutions involve pushing data to all of the nodes first, and others, actually that's about the only solution that I know of right now. So, I've set about to solve this, and my solution is, to the best of my knowledge, quite different from anything else out there. The pen tester, or attacker, starts with their word lists, and then runs them through whatever tool they wish to use. You can use John the Ripper, you can use the Hashcat CPU version, you can use custom Python scripts. You can also generate your guesses based on Markov chains, sentences, or any other particular technique that you so desire. The data from all of these is piped into the main network server on a port, currently 4444, and the server can listen to a large number of streams at once. So you can basically throw in whatever you want, it grabs it, processes it, and sends it out to either local devices in your system or remote clients across the network. So you can throw as many systems as you want at it, and within reason, it scales. It's obviously not as fast as doing word list mutation on the video cards, but for salted hashes with large hash lists or slow hashes, it's actually not a limitation. And the other thing that I've done with this is support lengths up to 127 for the algorithms that I've added so far, which, to the best of my knowledge, puts us in kind of a unique class. So, now I would like to shift gears slightly and go back to rainbow tables. They're still disturbingly relevant because very few people are actually salting their passwords. And as noted earlier in an earlier presentation, they are getting ridiculously large, difficult to transfer, and that's really been kind of a limit on the upper end of the rainbow table size. It's hard to shuffle multiple terabytes of data around the internet. And if one decides that they want to build length 9 rainbow tables, which are looking to be on the order of 10 terabytes, there's really no good way to move that. You can't even put it on external hard drives unless you're doing software RAID across them or other fairly difficult solutions. There's also the problem that they take forever to download. How many of you have tried to download a couple terabytes worth of rainbow tables? It's not a quick process. So my solution to this was something that I called web tables, and I used this slide at my DEF CON talk. However, I'm going to go into a lot more details, so we don't need that slide. For those of you who have not written or done extensive work with rainbow tables, I am going to go over a little bit of the candidate hash generation process because it's relevant to understanding this and understanding how it is different from some of the send your password out to a website to crack it solutions. Web tables theoretically allows you to submit, to use the web table service without disclosing your plain texts. I've talked with some people about some interesting potential attack models against it and would be happy to have conversations if other people have ideas, but it at the very least makes it difficult. So the first step in rainbow table cracking is the candidate hash generation. And this involves basically playing the what if game. What if the hash that I'm looking for was at position 0 in a chain? Well, we reduce it and we start the chain generation process. What if it was at position 1? We start it there and we run it through with the target hash that we're looking for at all of the possible positions in the chain, including the last position, at which point your target hashes would be sent across the network to the server. Most people really aren't comfortable with this for very good reasons, so the default is to just drop the last 2 chains. This is configurable, but now at the best case, the attacker has to go back a couple steps, which even for NTLM is difficult because many, many hashes will map down into the same password. So the next step in rainbow table cracking is doing the chain search or the table search. For my tools, because this improves performance on spinning hard drives, I sort the hashes into the table order. They get fed into a search process that looks through the tables on the disk and comes up with the chain start points, either numerically or ASCII or whatever your particular representation is. So what web tables does is simply replace the search on disk with queries to a remote server. What the web table search process looks like in much more detail is you start with the candidate hashes. They're in sorted order because in addition to making things easier on the remote server, it mangles the ordering and makes it more difficult for an attacker to figure out what's where. The next step is actually chopping them down. Rainbow tables don't need to store the full, say, 128 bits of output of MD5. If you can distinguish all of your endpoints from one another with 59 or 67 bits, then there's no reason not to do that because you don't lose any efficiency, but yet you save a good amount of storage space. So the web tables process chops the hashes down to their to the smallest value that the table supports, and concatenates them together in a giant HTTP post request. And this is all actually binary data, it's not the ASCII hex. So this gets sent up to the server, which then performs a number of calls to backend table servers. And this is completely irrelevant from the user perspective, other than to know that the web tables backend can scale to pretty much handle any level of load. Currently this load is 0, so it's not really a problem. But it can scale. And this is all done completely transparently from the user. When they get their results, the results are sent back from the web server to the client, which then takes these as the chains to begin regenerating and moves to the final stage, which is the chain regeneration and looking for the target hashes. So the default, as I said earlier, is to skip the last two candidate hashes. But this is user selectable. If you want to skip more, you can. If you want to skip less, you can. I chose 2 as a good default because for the current length 8 table chain length of 200,000, the loss in efficiency really isn't very significant. It's a flexible backend, so it can be scaled easily. It can have multiple servers going to it, and all of this is transparent to the end user, which is the goal. And finally, the biggest advantage of web tables is that there is 0 table download needed. You don't need to try and download a couple terabytes when there's only 2 peers. You don't need to try and download them on a residential connection. You can just go ahead and start using it and have full access to all of the tables instantly. So, that's about it for my presentation. Questions? I answered everybody's questions. Awesome. Yes, all of the stuff that I've talked about.
Repeat the question.
Oh, yeah, the question was, is the software for this available? All of the stuff that I've talked about is up in SVN. I don't have to clean anything up and release it in a couple months. This is all in the SVN repository available for use currently. I've got some of the back end for web tables. It's not an SVN because it's irrelevant to how it's normally used, but I do actually have a server script up in there that can be used and point to local stuff.
Do you have any plans on future development?
The question was, any plans on future development? Yes, I plan to keep developing it in the future. My goals right now that the multi-forcer framework is more complete and in a fairly mature state, are to start adding algorithm types. I'd also like to split out the build such that you can have a CPU-only build that could be deployed on, say, a corporate network as a Windows system service or as a tray icon on desktops. And yeah, with the Rainbow Tables stuff, I'm adding new algorithm support. I'm currently in the middle of generating SHA-256 tables, and we'll probably get around to adding some more algorithm types as they show up in the wild. If anyone wants to help, please contact me because it's really easy to add stuff.
Double SHA-256.
Okay, I have a request for double SHA-256. I don't think I want to know who's using that, but I'm sure somebody is because it's clearly twice as secure as regular SHA-256.